Hello, my name's Darren Holmes, and today in AC Electrical Circuits, we're going to be looking at lab number 6, Series RC and RL circuits. Under Objective, it says this exercise examines the voltage and current relationships in series RLC networks. Of particular importance is the phase of the various components and how Kirchhoff's voltage law is extended for AC circuits. Both the time domain and phasor plots of the voltage are generated. Now under reference sections, I'm referring to Sherman's Outlines, Basic Electricity, 2nd edition. So in chapter 15, we're looking at single phase circuits. We're going to review chapter 13 and 14. Chapter 13 is inductance, inductive reactance. And chapter 14 is capacitance and capacitive reactance. So in Sherman's Outlines, Basic Electricity, figure 14-16C is the time diagram of an RC series circuit, like we're going to be building today. And I just want to remind everybody that VR, the voltage across the resistor, and the current share the same phase. So we'll not be able to see current on the oscilloscope, but we can see the voltage drop across the resistor on the oscilloscope. And the phase angle of the voltage across the resistor is identical to the phase angle of the current flowing through the resistor. I just want to remind everybody that the voltage across the capacitor lags I by 90 degrees. So that means it's going to lag VR by 90 degrees. So you can see the voltage on the capacitor is 90 degrees out of phase from VR. And figure 14-17 is for a series RC circuit. And we can see that R is at 0 degrees, XC is at minus 90 degrees, and Z is the total AC resistance. So it's going to be at some angle from R. So in Sherman's Outlines, Basic Electricity 2nd edition, you can see figure 13-12 shows us the timing diagram of an RL series circuit. So I just wanted to remind you that VR, the voltage across the resistor, will share the same phase as the current. So we can't see current on the oscilloscope, so the phase angle for the current will be the same as the phase angle for the voltage across the resistor. Now VL is going to lead I by 90 degrees. That means the voltage across the inductor is going to lead VR by 90 degrees. So that's what we're looking for when we look on the oscilloscope. Okay. Figure 13-13 shows us the phasor diagram for an RL circuit, and you can see R is at 0 degrees, XL is at 90 degrees, and Z, which is the AC resistance component of the entire circuit, is going to be at some angle to R. And in chapter 15 they talk about single phase circuits, and they talk about RLC in series, which is what we're going to be working on today. And in figure 15-1, they give us the RLC circuit diagram, phasor diagram, and voltage phasor triangle for when XL is greater than XC. So this is basically an inductive type circuit. And in figure 15-2, they give you the phasor diagram and voltage phasor triangle for when XC is greater than XL, basically a capacitive circuit. And they provide you with the formulas that we're going to be using in the lab today. They cover impedance in a series RLC circuit. And figure 15-4 gives you the series RLC impedance phasor triangles. We have a brief theory overview stating that each element has a unique phase response, so we need to keep this in mind when we're doing our calculations and viewing the output signals on the oscilloscope. Under equipment, we're going to be using an AC function generator, which happens to be built into our oscilloscope, so we also need the oscilloscope and a digital multimeter. Under components, we're going to use a 1 k ohm resistor, and down the side of the page I have given you the color codes for it to make it easier to find in your parts kit. We also need a 10 millihenry inductor and a 10 nanofarad capacitor. My 1 k ohm resistor is actually 995 ohms. My 10 millihenry inductor is 22.3 ohms. And my 10 nanofarad capacitor is actually 13.45 nanofarads. So I filled in the equipment used. The AC function generator and the oscilloscope are both the KEYSIGHT EDUX 1002G oscilloscope. And the DMM is going to be the Mastech MSM 9803. Now I haven't bothered with the serial numbers. They're not going to be important for this particular lab. Under components, I've gone ahead and measured my 1 k ohm resistor, and it's 995 ohms. The 10 millihenry inductor, its DC coil resistance was 22.3 ohms. And a 10 millihenry inductor is labeled 103. So 103 is in microhenries. So 10 millihenries is 103 microhenries. The 10 nanofarad capacitor measured in at 13.45 nanofarads. And it's a non-electrolytic capacitor, which means it'll be labeled with a number like 103. And 103 refers to picofarads. So that ends up being 10 nanofarads. Remember, resistors have a tolerance of plus or minus about 5%, where capacitors have a tolerance up to 10% or more. Under schematics, we have figure 6.1, which is R and C in series. And in figure 6.2, we have R and L in series. Under procedure, step number 1, we're talking about the RC circuit. So we're going to be using figure 6.1 with Vin equals 2 volts peak to peak sine wave at 10 kilohertz. Our resistor is going to be 1 k ohms and our capacitor is going to be 10 nanofarads. We're to determine the theoretical capacitive reactance and circuit impedance and record the results in table 6.1. The experimental portion of this table will be filled out in step 5. We're then going to be using the voltage divider rule to compute the resistor and capacitor voltages and record them in table 6.2. Just a reminder, phasors are in RMS, but the oscilloscope gives us volts peak to peak, so we're going to leave our results in volts peak to peak. So I've created 2 calculation pages for you. The first part is for the RC circuit, where R equals 1K, C equals 10 nanofarad, Vn equals 2 volts peak to peak, and the frequency equals 10 kilohertz. I've already put the formulas in for you, and the formulas in for the voltage divider rule. So these are the calculations for the RC circuit, and I just wanted to mention that you have to follow the order of operations, so I've actually put parentheses around my items that I'm going to do the 1 over function of. So it's 1 over all of those things, so put parentheses or brackets around the entire thing. Same thing when you're doing the square root for the circuit impedance. Make sure that you put parentheses around them so that the order of operations stay intact. Most calculators don't have an arctan button, they have a tan to the -1 button. And remember to put parentheses around those two numbers when you're dividing them. Now when it gets to the voltage divider, we're going to use voltage divider for VC and VR. And remember, these are phasor numbers, so we need RMS values. So it's 2 volts peak to peak divided by 2 gets us to the V max, or the peak voltage, and then divide by the √2 to get to the RMS voltage. So when I do my calculations, I end up multiplying it by 2 volts peak to peak divided by 2 √2, and then for my answer I leave it as 1.69 volts peak to peak divided by 2 √2, because this is what we're going to see on the oscilloscope. So if you divide by 2 √2 now, when you take the reading off the oscilloscope, you'll have to divide it by 2 √2 to compare the two. So I just leave all my voltages as peak to peak. That way it makes it a lot easier for me to compare it to the voltage off of the oscilloscope. So under data tables for RC circuits, I've filled in my values for XC, the Z magnitude, the Z phase angle, BC magnitude and phase angle, VR magnitude and phase angle. So under procedure, RC circuit, step 2, we're going to build the circuit of figure 6.1. We're going to place one of our oscilloscope probes across the generator and the other across the capacitor. Set up our function generator at 2 volts peak to peak, 10 kilohertz. Under procedure, step number 2, it says build the circuit of figure 6.1, which I have here. R is 1K, so that's my 1K ohm resistor, and C is 10 nanofarads, and it is labeled 103. You'll notice I have a red wire coming in going to the top of the resistor, so this is where I plug in my function generator. I have a black wire going to the bottom of the capacitor, so this is where the common or grounds will be connected. I have a yellow wire at the junction of the capacitor and the resistor, so this is where I'm going to take my voltage reading across the capacitor. So this will be channel 2 of the oscilloscope, and the input will be channel 1 of the oscilloscope. So I just wanted to show you the connections from the oscilloscope. All the black banana leads go together into the orange terminal that go to the black lead that go to the bottom of my capacitor. Channel 2 of the oscilloscope goes to the yellow wire that goes to the junction of the resistor and the capacitor. The output from the function generator and channel 1 of the oscilloscope go through the red wire that goes to the top of my 1K ohm resistor. So I've powered up my oscilloscope. I don't know who used it last, so we need to set it up for a 10 kilohertz sine wave at 2 volts peak to peak. So as you know from previous videos, I like to do a default setup, and I like to select factory defaults and say OK, just so I have a common starting point. So the next thing I have to do is go to channel 1 and change some of these items. So the first one is coupling. I'm working with an AC signal. I don't want any DC on it. The lab mentions putting on bandwidth limit, so I'll put that on. And then my probe, right now it's set 10 to 1, and we use 1 to 1 probes in our lab. So I'll set it to 1 to 1. I'm going to do the same thing for channel 2, change its coupling to AC, bandwidth limit on, and the probe, we need to set that 1 to 1, or else it multiplies all our numbers by 10, and we don't want that happening. The next thing we want to do is put on the wave generator. So it comes up at sine wave 1 kilohertz. We need to select frequency and increase that up to 10 kilohertz. So there's our 10 kilohertz frequency. Amplitude, they wanted 2 volts peak to peak. So select amplitude and then adjust it up till it says 2 volts peak to peak. Make sure there is no offset on this because we don't want a DC component to our waveform. The next thing I'm going to do is check my amplitude per division. So this is channel 1. I've got it at 500 millivolts. If I go to 200 millivolts, it goes off the screen. So I'm going to bring it back to 500 millivolts. And channel 2 is at 500 millivolts. 200 millivolts, it also goes off the screen. So they're both set at 500 millivolts. Now my horizontal, right now it's at 100 microseconds. And I like to see 1 or 2 cycles on the screen. If I do 1 cycle, I can't quite tell if it's on the edge of the screen or not. So I'm going to bring it back so I can see 2 complete cycles so I know that this is on the screen. The next thing I like to do is get my measurements up. So I press the measure button. And this oscilloscope defaults to frequency for channel 1, peak to peak for channel 1. The next thing I need to do is add a measurement. So source channel 1, I'm going to press source and select channel 2. And then under type frequency, I'm going to select the type. And I want channel 2's peak to peak voltage. And then I'm going to select add measurement. So now I've got my frequency, peak to peak channel 1, peak to peak channel 2, and so I'm now ready to go and do the rest of my lab. So under procedure, step number 3, we're to measure the peak to peak voltage across the capacitor and record it in table 6.2. Along with the magnitude, be sure to record the time deviation between VC and the input signal, from which the phase may be determined. We're going to be using the math function, measure and record the voltage and time delay for the resistor. And they show us that this is going to be equal to Vin minus Vc. They want us to compute the phase angle and record these values in table 6.2. So under procedure, step number 3, we're to take some measurements. The first one is the voltage across the capacitor. So if you've set up your measurements on the screen, we can see at a frequency of 10 kilohertz, the peak-to-peak voltage on channel 2 is 1.79 volts, and that's the voltage drop across the capacitor. The next thing we need to do is find out what the time deviation between the input signal and the voltage drop across the capacitor is. So the easiest way to do that is with our cursors, so I'm going to show you how to do that now. So press the cursor button in, and we can see that we have the cursor menu down the side here, but it's not the entry knob that changes the cursor positions. It's over here, the knob beside cursors, that allows us to change our cursors. So source, we usually use channel 1 as the source, and then we can select the individual cursors, but rather than selecting it here, we can also select the individual cursors with this knob. So if I press the knob in, it allows me to select the different cursors. So if I select X1, and now I can start moving the cursor, and you'll notice it starts at the far left-hand edge and moves in. So I'm going to move X1 until it comes to the first waveform, which is the yellow waveform which is my input signal. So I want to put that cursor right on the 0 crossing. Then I'm going to press the knob in again, and this time I'm going to select X2. And now when I rotate the knob, you can see the cursor on the right-hand side of the screen starts moving. So as I move it in, I want to move it over to the green waveform, which is channel 2, and I want to get its 0 crossing. So remember, this is the X cursors, so X1 and X2 cursors. So the time deviation is actually 7.8 microseconds because we get delta X. So delta X is the time difference between cursor 1 and cursor 2, or X1 and X2. Now it might be hard to see exactly where those 0 crossing lines are. So what I do is I come along and I change my horizontal. So I actually open up the waveform. Now it will go off the screen, but all I'm interested in is these 0 crossing points. So the next thing I do is change my amplitude. So I want to get the waveform crossing vertically. Now it's gone way off the screen, which is perfectly okay. But all I'm interested in is those 0 crossing points. So now I can adjust my cursors. So this is X2. I can get it to exactly where that green trace crosses the 0 line. And then pressing the button, I can go back and select X1. And then put it exactly where it crosses that 0 line. So in this case, my delta X is 7.82 microseconds. Now I want to show you one more feature of this oscilloscope. I'm going to put the horizontal back to where it was. So I see a couple of waveforms. And I'm going to reduce the amplitude for the vertical back to where it was. And one of the things that we can do with this is directly calculate phase angle. So in order to do that, the first thing I'm going to do is change my cursor so it starts on a 0 crossing. So I'm just going to take channel 1 where it crosses the 0 line. And then I'm going to select X2 and move its line to the exact same position. So you'll notice I haven't gone on a positive going edge, I've gone on a negative going edge. So these are sometimes hard to set up. You might have to go back and readjust it. So now I've got X1 and X2 covering the entire waveform, and that's just channel 1. You'll notice it's 100 microseconds, and 1 over 100 microseconds is 10 kilohertz, which is what we expected to see, because we do have a 10 kilohertz signal here. So it's extremely important that you have X1 going through channel 1, a 0 crossing. We call this a negative going crossing. So X2 has to be at the second negative going crossing. Delta X, or the distance between those two 0 crossings, is 100 microseconds. And 1 over delta X is 10 kilohertz, which is what we expected since we put this frequency into our function generator. Now the next thing I'm going to do is I'm going to go and make sure that cursors, and I have the cursors menu showing down the side of my screen. I want to go to units, and under units, at the top here, it says X units seconds. So I'm going to select it, and I'm going to go down to where it says phase. So you notice the numbers changed at the bottom of my screen. Now we're going to use the X cursors as 360 degrees. So if I press that button in, it tells me from X1 to X2, that's 360 degrees. And remember, a complete cycle of a waveform is 360 degrees. So then I'm going to go back to my cursor knob, and I'm going to select X1, and I'm going to move it over to channel 1 where it crosses the 0 line. And then I'm going to select X2 and move its cursor over to where the green trace crosses the 0 line. So it's very important that when you're doing a phase measurement that both waveforms are either positive going or negative going. Don't try and select a negative going and a positive going. It doesn't work that way. What we want is the time difference between the two waveforms. And here we can see that delta X is 28.8 degrees. So that's the shift between the input signal and the voltage dropped across the capacitor. Remember, this is voltage drop across the capacitor. It's not current through the capacitor. So continuing on under procedure step number 3, we now want to measure the voltage drop across the resistor. So what it says is, using the math function, measure and record the voltage and time delay for the resistor. That's Vin minus Vc. And then we're going to compute the phase angles, record these values in table 6.2. So just to remind you on how to do that, we did do that in lab 3, how to use the oscilloscope. So what we do is we go to the math function, and we have function f at t. The operator, right now it's on plus. We need that operator to be minus. So the source is channel 1. Source 2 is channel 2. And we'd like to have it on the same scale, because right now it looks like it's larger. So when you subtract the two waveforms, it should actually be smaller. So I'm going to change my scale so that it too is on 500 millivolts per division. Now it has an offset on here, so make sure you do click on the offset and get rid of that offset. Put it at 0 volts, or else some of your measurements are going to be wrong. Now we'd like to know what the peak-to-peak voltage is, because that represents the voltage drop across the resistor. So what we have here so far is all our deltas. So I'm going to go back to measure. So press its button in, and you can see I've got frequency for channel 1, peak-to-peak channel 1, and peak-to-peak for channel 2. So now I'm going to select source, and we can select the math source. So then the type is peak-to-peak, which is what we want. So I'm going to add that measurement. So now we have our measurements at a frequency of 10 kilohertz. Our input voltage is 2 volts peak-to-peak. Mine says 2.05. Channel 2 peak-to-peak, 1.79. That's the voltage drop across the capacitor. So remember, that's that one. And then the peak-to-peak for the math function, it has a little m in there, is 1.02 volts. And that's the pink trace right here. So the pink trace is the voltage drop across the resistor. It's also the phase angle for the current going through our circuit, because voltage and current going through a resistor share the same phase angle. So the voltage drop across the capacitor should be 90 degrees out of phase with the voltage drop across the resistor. So that looks like it's correct. So the next thing we need to do is determine what the phase angle is between the voltage drop across the resistor and our input voltages. So to determine the phase angle between the voltage drop across the resistor, which is our math function, and the input voltage, which is our yellow trace, we need to go back to cursors. And right now it says cursor 2, so I'm going to press the button in, and I'm going to select X1, and I'm going to move that cursor over until it gets to the positive going transition, going through that zero crossing point. So that's a positive going transition, so I'm going to measure it between the positive going transition of our input voltage. So I'm going to press the cursor knob in again. I'm going to select X2. I'm going to move its cursor over until it gets to that yellow trace. So it looks like delta X in this case is actually 17 microseconds. Now in the previous case where I was measuring delta X for the phase angle between VC and the input voltage, I actually increased my volts per division so that I could get a more vertical looking line. But notice when I increase it, and it goes off the screen, my pink line changes wave shape. It's because it's doing the calculation based on what's shown on the screen, and where it goes off the screen, the result is 0. So I cannot, in this case, adjust my vertical to get a better zero crossing. So what I'm going to do is leave it at 500 millivolts per division, and assume that's the best case scenario for taking this measurement at 17 microseconds. So as I did in the previous case, I'm going to move my cursors. So right now I'm on X2. So I'm going to move that over until I get the negative going transition of my input voltage. Change it to X1. Move it back until it goes through the negative going transition. So you can see I've set it back to 100 microseconds or 10 kilohertz between the negative going transition of channel 1, which is the input signal. So I'm going to press units, and up here where it says X units, I'm going to select phase, and then I'm going to use X cursors at 360 degrees. So now you can see my delta X is 360 degrees. So now I can go back and reposition my cursors. So X1 is going to go through the positive going transition of VR, which is the math function. And X2, I'm going to reposition for channel 1, which is the yellow trace, where it goes through the zero crossing. And we can see the delta X, in this case, has come out to be 61.2 degrees. So you can see under table 6.2, I've recorded my experimental magnitude for VC is 1.79 volts peak to peak. And you can see that compares to my theory of 1.69 volts peak to peak. And I've recorded my experimental magnitude for VR as 1.02 volts peak to peak. and you can see the theory was 1.06 volts peak to peak. So doing the calculations beforehand tells you whether you're getting close to the right results or not. Now I have the experimental delays recorded here. For VC, I recorded 7.82 microseconds as being the most accurate reading. And for VR, I recorded 17 microseconds. The formula for calculating phase angle is delta T, or the time difference between the applied voltage in VC or VR, divided by the period. And remember, we're using a 10 kilohertz signal, so the period is equal to 1 over the frequency, so that's equal to 100 microseconds. So to calculate the phase angle for VC, I take the 7.82 microseconds, divide it by 100 microseconds, and multiply that by 360 degrees. So the result is 28.15 degrees. Now to calculate the phase angle for VR, it's the 17 microseconds divided by the 100 microseconds times 360 degrees. So you can see the experimental phase angle for VR works out to be 61.2 degrees. Now you'll notice in our calculation for VC, it was a negative angle. So let me show you why that happens on the oscilloscope. So you'll remember back in lab number 2 on phasor and vector review, I had this little graphic here on leading plus 90 degrees versus lagging minus 90 degrees. And when you take a look at the solid waveform and compare it to the dotted waveform, the dotted waveform is actually leading by 90 degrees. When we're looking at the dotted waveform, comparing it to the solid waveform is actually lagging by 90 degrees because it happens after. So when we're working with RC or RL circuits, we need to remember whether the current is leading the applied voltage or lagging the applied voltage. So I've gone out on the internet, and at this web address down here, gsu.edu, they're showing a mnemonic, and it's for the phase relationship of current and voltage. And it's called Eli the Iceman. So under here we can see Eli in an inductor, voltage leads the current. And over here in a capacitor, the current leads the voltage. So Eli the Iceman is a nice handy mnemonic so you can remember whether current's supposed to lead or lag. So the last thing we need to do is look at these phase angles and determine whether it's going to be a positive or negative phase angle. So the yellow trace is channel 1, which is our input voltage. The green trace is the voltage drop across the capacitor. So if the center line is time 0, we can see the green trace goes through the 0 crossing at some later time. So VC is said to be lagging the input voltage. The pink trace, which is channel 1 minus channel 2, which represents the voltage drop across the resistor, is happening before our applied voltage, or the output of the function generator. So it is said to be leading. So leading is a positive angle, lagging is a negative angle. So the phase angle for VC is minus 28.15 degrees because that's the voltage across the capacitor, which is channel 2 and is the green trace, and it is lagging the input voltage. And the phase angle for VR is positive because it is the math function, and it was the pink waveform, and it was actually leading the applied voltage. Under procedure, step number 4, it says with the oscilloscope displaying Vin, Vc, and Vr, we're to sketch the waveforms on oscilloscope plot number 6.1. Now we need to sketch these waveforms, and it's extremely important that all our 0 volt lines line up on the center line. If you have any of your vertical position knobs adjusted, so I'm going to adjust channel 1, and you can see that the waveform moves upwards. But as it moves upwards, you can see it changes the 0 crossing. So on the left-hand side here, you can see the 2 ground symbols are separated. So to put it back to the 0 crossing quickly, you can just press the position button, just press the knob in, and it will drop it down to the 0 crossing line. So we need to sketch these waveforms, and it's very hard to sketch all 3 at the same time. So what I like to do is start by turning off my math button. So that got rid of the pink line. And then I'm going to press channel 2. And that gets rid of the channel 2 trace. So now I can sketch this waveform fairly easily. I can find out where the 0 points are on my plot, and then I can find the peak, and then I try and draw my waveform best fit as possible. Remember, it's not a triangle wave, so try and get some curve at the top and the bottom. Once you've drawn in E, or the applied voltage, you can bring in channel 2. So now you can plot channel 2 on your graph versus the applied or input voltage. So channel 2 needs to be labeled something so you'll remember it later, and channel 2 happens to be VC. Once you've drawn in channel 2, you can turn off channel 2, and then we can go back and press the math button, and it brings in the pink trace. So now you can sketch the pink trace in relation to the applied voltage. Remember, the pink trace needs to be labeled, and we will label it VR. So when you've finished your sketch, it should look like what's being displayed on the oscilloscope screen. Don't forget to record your volts per division for channel 1 and channel 2, and your time per division for the horizontal scale. So I've sketched in the waveform from channel 1. I did it by putting in the 0 crossing points first, and then saying where the peak were on each of these grid positions, and then I tried to sketch in a waveform that looks more like a sine wave than a triangle wave, and then I labeled my sine wave as being Vin. So I've now highlighted my channel 1 waveform, and that was Vin, and I've sketched in my channel 2 waveform, and channel 2 is the voltage drop across the capacitor, so I labeled it VC, and you'll notice that I've drawn it in showing that it is actually lagging the input waveform. So I've now highlighted my channel 2 waveform with the green highlighter, and it is VC. And now I've sketched in my math waveform, which is channel 1 minus channel 2, and Vin minus Vc gives us the voltage drop across the resistor. So you'll notice I sketched it in by putting in the zero crossing points first, and then drawing in the peaks and valleys. It gets a little bit complicated when you've got 3 waveforms on your screen at once. So under procedure, step 5, they want us to compute deviations between theoretical and experimental values in table 6.2. And what we're going to be doing is, based on the experimental values, they want us to determine the experimental Z and XC value via Ohm's law. So I equals VR divided by R, XC equals VC divided by I, and Z is equal to Vin divided by I. And we're supposed to record these into table 6.1 along with the deviations. So for the RC circuit, we're going to use Ohm's law, and I just want to remind you that it is V equals IR. So rearranging our formula, we can see that I is equal to VR divided by R. XC, which is resistance, is equal to VC divided by I. And because it's a series circuit, it's the same I going through R and C. And then Z is our total resistance, so that's equal to Vin, or our total input voltage, divided by our current. And in a series circuit, total current is I, and it's the same going through the resistor and the capacitor. Now, I don't think I gave you this formula, but for the phase angle, theta, it's equal to arctan of minus Vc divided by Vr. So now I'm going to plug my measured values and my experimental magnitudes into these formulas to get my results. So for VC, my experimental magnitude was 1.79 volts peak to peak, and VR was 1.02 volts peak to peak. So keep in mind we recorded these as peak to peak values, so our results will also be peak to peak. So you can see for my calculations, I is equal to 1.02 volts, that was peak to peak, divided by my resistor, and that's the measured value of my resistor, and that came out to be 1.025 milliamps. Then to calculate XC, I took the VC peak to peak, which was 1.79 volts peak to peak, and divided it by my current from above, which is 1.025 milliamps, and keep in mind that's also peak to peak. So the peak to peaks cancel each other out, and you're left with 1.75 k ohms. And then for Z, I take my total voltage that was applied to the circuit of 2 volts, my total current going through the circuit, which is 1.025 milliamps, and that worked out to 1.95 k ohms. And then for my phase angle, remember, your calculator probably says tan to the minus 1 on it. So I took the minus 1.79, dividing it by the 1.02, and that worked out to approximately 60.3 degrees negative. So summing all this up in table 6.1, you can see XC was 1.75 K compared to my theory of 1.59, so that looks like it's about a 10% deviation. My Z magnitude, now remember this is the total impedance of my circuit. Mine worked out to 1.95 K, and in theory we had 1.88 K, so that looks pretty close. and my phase angle, and it looks like 60 degrees versus 57 is pretty close again. So all these percent deviations I'm going to leave you to figure out. Remember, if you're getting 20% or more deviation, you've probably done something wrong. Under procedure, step number 6, we're to create a phasor plot showing Vin, Vc, and Vr on phasor plot 6.1. Remember, phasors are in RMS, but the oscilloscope gave us volts peak to peak. So at this point we must convert our answers using V peak to peak divided by 2 root 2. So to draw the phasors for plot 6.1, the first thing we have to do is convert all our peak to peak numbers into RMS values. So Vin was 2 volts peak to peak. You divide it by 2 to get the maximum or the peak voltage, and then by root 2. So that should come out to 707 millivolts. Try and keep things in proper engineering notation. That is 0.707 volts, right? So 707 millivolts. My VC is 1.79 volts peak to peak divided by 2 root 2, so that works out to 633 millivolts, and I just rounded that up. VR is 1.02 volts peak to peak divided by 2 root 2, and that worked out to 361 millivolts. And then the current, 1.025 milliamps peak to peak divided by 2 root 2, came out at 362 microamps. So to draw the phasor diagram for plot 6.1, we start by drawing I on the horizontal axis, and VR is in phase with I, so on the horizontal axis I'm going to draw VR. Now VR is 361 millivolts, so I'm doing about 100 millivolts per division, so 100, 200, 300, and approximately 61. You don't have to be 100% accurate. Remember, VC, that's minus J, so VC goes down 90 degrees. So in my case, VC was 633 millivolts, so 1, 2, 3, 4, 5, 6, and about a third of a division. So drawing our rectangle box in, that I've drawn in with these dotted lines, where they meet, that will be Vin. So you'll notice that Vin is actually at a phase angle, and that phase angle is the 61 degrees that we calculated earlier, and the phase angle between VC and Vin is minus 28 degrees. So this is the completed phasor diagram for plot 6.1. So under procedure, step number 7, we're now working with the RL circuit. So we're to replace the capacitor with the 10 millihenry inductor, and we're now using figure 6.2, where R is in series with L. We're to repeat steps 1 through 6 in a like manner, using tables 6.3 and 6.4, and sketch the oscilloscope waveforms and phasor diagrams on plot 6.2. So you notice on the schematic, figure 6.1 and figure 6.2 look almost identical, except we're going to replace this capacitor with the inductor in our circuit. So under procedure, step number 7, it says to replace the capacitor with the 10 millihenry inductor. So I've pulled out the 103 capacitor and replaced it with the 103 inductor. So these are my calculations for the RL circuit, and once again I want to remind you to put brackets around your numbers so that you can keep the order of operations intact. And when you get down to the voltage divider for the RL circuit and we calculate VL and VR, I just want to remind you that I left my answers as peak-to-peak voltages divided by 2√2 so that I can compare these to the oscilloscope readings. So in table 6.3 and 6.4, I've filled in my calculations for the RL circuit, XL, Z magnitude, and Z theta, and VL magnitude and theta, VR magnitude and theta. So all I've done is I've replaced my capacitor with my inductor, and I haven't changed any settings on the oscilloscope. So you can see that the yellow trace is my input voltage or my applied voltage, and at the bottom here it's 10 kilohertz at 2 volts peak to peak. The green trace is the voltage drop across the inductor, and you can see it is leading the input voltage, and the peak to peak voltage for channel 2 is 1.07 volts, and the math function is actually lagging the input voltage, and this is the voltage drop across the resistor. So you can see it is 1.69 volts. Now to take the phase measurement, I'm going to turn off the math function. So now I'm just left with Vin versus the voltage drop across the inductor. So I'm going to put on my cursors, and I'm going to go to the knob for cursors, and I'm going to adjust X1. So I want to make sure first off that I have the correct 360 degrees setting. So X2 will go to the other zero crossing. So you can see from the beginning of my waveform through one complete cycle is 360 degrees that I'd set up previously. So now I can adjust my cursors. So X2 is going to go to where the input voltage crosses the zero line. And then I'm going to select X1 and move it over to the green trace of channel 2, which is VL. So I think mine's about there, so I'm going to record that as 56.88 degrees. Now keep in mind, right, for the lab we need that to be in time divisions or seconds. So I'm going to go into my units, and at the top where it says X units phase, I'm going to change that back to seconds. So you can see my delta X is 15.8 microseconds. So that's what I'm going to record in table 6.4. Now I need to bring my math menu back up because I need the math function because this is the voltage drop across the resistor. And I'm going to turn off channel 2. So now I need to readjust my cursor lines. So X1, I need to be going through the zero crossing for channel 1, which is my input voltage. And X2 needs to go through that pink trace, or VR. So I'm going to adjust it and try and get it right on that zero crossing line. And I'm going to record that as 8.4 microseconds. Now you can go back to the cursor menu, and where it says units, X units, you can change that to phase, and you can see that's 30.24 degrees. Now I just want to remind you that when the waveform is to the right of the input voltage, it is said to be lagging. So in this case, the angle of 30.24 degrees is recorded as minus 30.24 degrees in table 6.4. So under table 6.4, for VL experimental magnitude, I've recorded 1.07 volts. And for VR experimental magnitude, I've recorded 1.69 volts. For VL, the experimental delay was 15.8 microseconds. And for VR, the delay was 8.4 microseconds. For the phase angle, you can compute it by taking the 15.8 microseconds, dividing it by the 100 microseconds times 360 degrees, or as I showed you in the video, we can take it directly off the oscilloscope screen, and that came out to 56.88 degrees. Now keep in mind, the voltage drop across the inductor was actually leading, or on the left-hand side of our input voltage. So it's positive. The phase angle for VR, which was the pink line, which was the math function, can be calculated as 8.4 microseconds divided by 100 microseconds times 360 degrees. Now in this case it was lagging, or to the right of the input waveform, so it's negative, and it's negative 30.24 degrees. Once again, I'm going to leave you to calculate the percent deviation between the magnitudes and the phase angle. So looking at the calculations for the RL circuit, we're going to be using Ohm's law, which is V equals IR, and rearranging the formulas. I is equal to VR divided by R. And remember, the phase angle for current is the same as the phase angle for the resistor. XL is going to be equal to VL divided by I. And Z, which is the total resistance of the circuit, is V in divided by I. And the formula for the phase angle is arctan of VL divided by VR. I don't think I gave these formulas to you in the procedure, but I'll give it to you now. So on table 6.4, my experimental magnitude for VL was 1.07 volts, and for VR it was 1.69 volts. So looking at my calculations for I, it's 1.69 volts peak to peak, divided by my measured resistance of 995 ohms. So that worked out to 1.698 milliamps. For XL, it was 1.07, so that was VL, divided by the current above, which is 1.698 milliamps, and that worked out to 629.97 ohms. And for total impedance of the circuit, we take the 2 volt peak to peak that we applied to the circuit, divide it by the current, 1.698 milliamps, and that worked out to 1.177 k ohms. So looking at the final results in table 6.3, you can see my XL was 630 ohms compared to the calculated 628 ohms. So this was a lot closer. My Z magnitude, 1.177, pretty darn close to the 1.18 k ohms. And the 32.34 degrees, very darn close to that 32.14 degrees. So remember, if you're getting a deviation of 20% or more, you've got some problems with your circuit, so I would check it over. And I'm going to leave you to do all the percent deviation calculations for this particular lab by yourself. So to sketch this waveform, I'm going to turn off the cursors because they're confusing. I'm going to turn off the math function, and I'm going to turn off channel 2. So right now I'm looking at the applied voltage, or the input voltage. So I'm going to sketch that first. Then I'm going to bring in channel 2, and channel 2 is the voltage drop across the inductor. And because it's left of my input voltage, I can say that it is leading. So then I'm going to turn off channel 2, and I'm going to put on the math function. So the pink waveform is the math function, or channel 1 minus channel 2. And in this case, it's the voltage drop across the resistor. So the voltage drop across the resistor is shifted to the right, and when it's on the right, we say it's lagging. So I just wanted to show you my finished oscilloscope plot for VL versus VR. I started by putting V in on the screen all by itself and drawing it as my reference waveform, and I've highlighted it in yellow here and labeled it V in. Next, I sketched in channel 2 in relationship to V in, so channel 2 was VL, and you can see I've sketched that waveform in, and don't forget to label it VL. You'll notice VL is actually leading V in. So then I turned off channel 2 and I put on the math waveform. The math waveform is VR. So I sketched in VR in relation to V in, and you can see that VR is lagging V in. I highly recommend that you highlight each of these waveforms so that you can tell them apart easily when you come back later to check your plots. So in order to plot our phasors on plot 6.2, the first thing we need to do is convert our results into RMS form. So Vn was 2 volts peak to peak. You divide it by 2 root 2 and it comes out to 707 millivolts. VL was 1.07 volts peak to peak, and that works out to 378 millivolts. VR was 1.69 volts peak to peak, and that converts to 598 millivolts. And our current was 1.698 milliamps, and that converts to 600 microamps RMS. So it's the RMS values that we actually plot on a phasor diagram. So to draw the phasor diagram for plot 6.2, I start by putting I on the horizontal axes, and VR is in phase with I, and VR was 598 millivolts, so almost 1, 2, 3, 4, 5, almost 6 divisions. VL, remember VL is the plus J in the formula, so VL is up 90 degrees, and in this case VL was 378 millivolts, so 1, 2, 3, and not quite 4 divisions up. Then drawing in our rectangle with these little dotted lines where they meet, this is our input voltage, and it goes from the 0 point to where the 2 lines meet, so that's V in. And you'll recognize these angles again. The angle between V in and VL is 57 degrees, and between V in and VR is minus 30 degrees. So this is the completed phasor plot for plot 6.2. As with all labs, we have some questions to be answered at the end. In this case, we have 4 questions, and the answers will be based on your results. When you've completed your lab, show it to your instructor so that they may initial it to indicate that it is complete.